This is lecture number 24 of the course AU203 Statistics and Quality Control, and in this lecture we will talk about central limit theorem. Before going into central limit theorem, we will look into calculating the mean and variance of some of the random variables. We already have deal with the linear combination of random variables, so sum of random variables would be exactly the same as the linear combination of random variables. And then we will develop the concept of central limit theorem, and after that we will be able to define the central limit theorem, and we can solve a problem related to that. Okay, suppose that we have a random sample of n observations taken from a normal population, and x is representing a random variable. So x can take different values. It can take x1, x2, x3. Since this population belongs to a normal distribution, and the mean and the variance of the population is mu and sigma square. Let's say we represent the sum of these random variables with the letter capital S. So capital S is nothing, the sum of all those random variables from x1 to xn. If we have to calculate the mean value of that random variable, so we just take the expected value of the random variable S, which is a sum of x1 and x up to xn. So all these expected values, as we know that x1, x2, xn all belongs to a normal population with mean, mu and variance sigma. So according to the reproductive property of normal distribution, the sum of random variables would also be following the normal distribution. So here the expected value of x1 would be mu because it belongs to a normal population. Similarly, for expected value of x2 would be mu, and so on. So altogether we have n terms. So the expected value of the sum of the random variables s would be equal to n times mu. So n is the number of random variables we are summing up. So this would become the formula for expected value of sum of random variables, which is just multiplying the number with the mean value of the population mean. Similarly, we can work out the variance of the sum of the random variables by adding up the variance of each random variable. Since according to this reproductive property of normal distribution, the sum of random variables would also be following the normal distribution, with each variance of x would be sigma square, and we have n times of that, so the variance would be n times of sigma square. And these are the means and the variance when you're dealing with the sum of the random variables, and all these observations have been samples have been taken from a normal population. Okay, now let's see the problems related with sum of random variables. Here the problem is the time it takes a randomly selected rat of a certain subspecies to find its way through a maze. So maze is sort of entanglement where you go from one end and you need to leave to the other end. So here the time the particular species of a rat takes is a normally a distributed random variable with mean value of 1.5 minute and standard deviation of 0.35 minutes. So what is the probability that the total time for 5 rat is between 6 and 8 minutes? So let x is a random variable that denotes the time in a maze in minutes. As we know that the time to find the maze is a random variable with normal distributed with mean 1.5 and variance 0.35 square. So let x1, x2 denotes the time in the maze for 5 different rats. So x1 is the random variable associated with time which ret 1 took, and similarly x2, x3 and x5 for these 5 rets. The total time for these 5 rets would be the sum of these individual random variables. And in the problem, what is given is the probability that the total time is sum of all the times, so x1 to x5 would be lying between 6 to 8 minutes. So over all these 5 reds, what is the probability that the sum of the time taken for rat to go through the maze is s, and that s is lying between 6 and 8. Okay, so the first thing is we need to calculate the expected value of the sum of those random variables, which would be n times mu. Mu is already we know 1.5, and 5 times 1.5 would be 7.5 minutes, would be the mean for 5 reds. Similarly, for variance would be for that sum of random variables s. The subscript small s is represent the sum of the random variables. So that would be n times sigma square, and sigma square is we know 0.35 whole square, so it would be 0.6125. So once we know the variance, we can find out the standard deviation. So probability can be worked out using the normal standard normal distribution, where it's s is the total time for 5 rats to cross the maze is s, subtract with its mean value and divided by the standard deviation to get the particular z value. And since s values from the problem, it should lie between 6 and 8, so substitute s6 here and mean 7.5 and standard deviation 0.783. So corresponding to these z values, we can work out the probability from the table or from the software. It comes out to be 71% is the probability that the total time would be between 6 to 8 minutes. So this is how we can solve problems related with sum of random variables. Let's say we have a distribution of average score from a fair dice. So as you know, dice has 6 possible outcomes. Either you get 1 or 2 or 3. So as you know, 1 upon 6 is the probability that you get 1 if you throw a 1 dice. So the distribution of this probability, if you throw a dice once, would be a uniform distribution. Let's say if we throw a dice 2 times, so when 2 dice are thrown and the possible outcomes are always 1 from 6. So if you see the distribution, probability distribution, so it looks like this. So 3.5 is more expected, or some highest frequency for to get it. And then if we throw the 3 dice, then your distribution looks like close to normal distribution. And if you increase the number of dice, let's say for 5 dice, then you have a better looking normal distribution. Or if you put a 10 dice, then your probability distribution looks like normal distribution. So there is a link when you're throwing dice several times, then your distribution is becoming normal distribution. And this you can see it from your throwing experiment of throwing a dice. Let's say another example in which in 1980 large companies CEOs made an average about 42 times that workers earned. So the average salary of the CEO is in 1980 was 42 times of the average salary of a worker. What happens in next 2 decades from 1980 to 2008? This score has jumped up to 42 times to 344 times. So there is a huge difference between a worker salary and CEO salary. So the distribution of the composition of Fortune 500 company CEOs for 2010 is plotted in this diagram, and you can see here these are the number of CEOs, and this is the millions of dollars of compensation, obviously annual compensation, annual earning from CEO. So you see most of the people would be lying, having a salary of around this is something $6.5 million. And then you see some of the CEOs would be earning quite a lot. So there is some asymmetric distribution as you see the salary of CEOs, different CEOs. So if you see this box plot, then you can see this is the minimum salary, and this is a lower quartile, and this is the middle one is a median value, and this is an upper quartile. And the rest of the things, the exceptional number of salaries could be an outlier because it can go up to 125 million or 130 million dollars. So that could be very few in numbers, but most this is about total 500 in numbers. So most of the salaries would be lying, the central tendency would look like this value, something like this value. So this would be the central tendency of the data. So you see there is always certain distribution present, and this time it is very much rightly skewed. So you can see very few people have higher salaries, and all these points can be considered as an outlier because these are some exceptional salaries which very few CEOs are getting it. So this would be a typical distribution. Okay, let's say we simulate this sample distribution of the means for 100 samples of different sizes. Let's say our sample size is 10. So we have a certain population, we are not sure about its distribution, but if we try to show the mean salaries or a mean of that population, then the sample means, because for a very large population you take some of those samples and you are plotting the mean values of those samples. So you got that particular sort of a distribution. If you increase the sample size, let's say the sample size increased from 10 to 50, so from that same population your sample mean distribution looks like this. So it is going towards normal distribution. If your sample size is increased to 100, and then the sample whatever the distribution is, population distribution is, but their sample means would be look like normal distribution. So if you increase further, then we can see that the distribution of the sample mean. So sample mean is the same thing. We have a population and we take several different samples, and I will show you later from the simulation that is given on this link that how for a given distribution, if you take a sample and the resulting distribution comes out to be normal distribution. So I will try to show you from this simulation. Okay, so if you look at this link which I have given an online stat book, and there is a sampling distribution applet, the Java applet that is available. For example, on the top you see there is a parent population, and right now it is a normal distribution. If I want a uniform distribution, it looks like a uniform distribution. If like a skewed distribution, you could like a skewed distribution, or you can generate your own distribution. Just like, for example, this is by clicking the mouse I can have this distribution. So I can draw any type of distribution. So let's say first start with the normal distribution. Let's say we have a normal distribution here. So what I'm going to do in the first step, I want okay, first clear this. First I want to have a sample, 5 samples out of that population. So I just click on animation, and here I just put 5 here. For example, I just want it 5 samples to be taken. So out of this population, once I put click on animation, what I'm going to get, I get randomly 5 samples out of that. And in this second graph, I see the mean value of those samples. So whatever the data is, I have taken 5 samples and I draw the mean value. So if I just clear all this and again I take 5 different samples, so this time I took a different samples, and the mean of that sample would be plotting somewhere here. So if I just clear it again, let's say again I animate 5 samples out of that. So only 5 samples, and then the mean would be this. So if I repeat this process, let's say 10,000 times, then what will happen is the distribution becomes a normal distribution. And if more times I choose the sample, then you see the central tendency would be exactly the same as the mean of that distribution, and the distribution looks like a normal distribution. So this is just a representation of the property of reproductive property of normal distribution. So if your distribution is normal and you take a sample from that, and we can have a better distribution if, let's say, if my sample size increased to 10. Let's say if I increase the sample size to 10. So let's say first I take 10 samples out of that population. I just took 10 samples, and this would be the mean value of that sample. And if I repeat that process 10,000 times, let's say, so I got this distribution. Let's say if I repeat the process 1,000 times, so I get this normal distribution. And you see, as my sample size is increasing, the variance of my distribution decreases. Let's say my sample size goes to 20, and I just take it first 5 samples from this place, and actually 20 samples rather. I have taken 20 samples, and the mean of the 20 samples looks like this. And if I repeat that process 10,000 times, the distribution looks like this. So you can see 10,000 times and your distribution looks like this. So it is not that strange. If you took another distribution, let's say instead of, you have another distribution like uniform distribution, and if you take 5 samples, let's say I just draw first 5 samples out of that. So I get 5 samples from that population, so mean value would be this. And if I repeat the process, I'm going to get a normal distribution. So this is actually the central limit theorem is whatsoever the distribution is, if you take the samples so many times, then the resulting distribution would be following a normal distribution. So let's say I can make it a skewed distribution like this, and if I take 5 samples out of that, so, and since the mean is plotted here, and if I repeat that process 10,000 times, so I'm going to get this would be the mean value, and this would be the mean value of this distribution. If you increase the sample size, let's say up to 20, and if you want to do it 10,000 times, then your more the sample size, the variance is decreasing, and the distribution would remains the normal distribution. So this is actually a basis, and I can have my own custom distribution. Let's say my distribution looks like anything like this, something like this. So if I take it a sample, 5 samples out of that, I can get 5 samples from that population, and so mean of that would be like this. If I do this process 10,000 times, then my resulting distribution would be a normal distribution. So this is the essence of the central limit theorem. Okay, now look into formally the definition of the central limit theorem. Let's say if x bar representing the mean of the random sample of size n observations is taken from this population with mean value mu and the variance sigma square. then the limiting form of the distribution as n approaches large number infinity would be the standard normal distribution. So it is exactly the same. Let's say whatever population you have, if you take a random sample and you calculate the mean, and now you are plotting the distribution of the mean. So this is the distribution of the mean would look like a normal distribution, standard normal distribution, with the mean would be mu, and the variance would be sigma square over n, or standard deviation would be sigma over under root n, and this z value would be following a standard normal distribution. So this is just a same way of what I have explained you in the simulation, that we have different distributions, and if you take samples from those distributions and calculate the mean value, and the resulting mean, if you do it several times when n approaches infinity, and then you end up with the normal distribution, standard normal distribution. So this we can visualize from this place as well. Let's say this would be your population distribution. So your population distribution would be something non-symmetric here. Let's say if we plot its distribution of the sample mean. So x is the population and x bar is representing its mean value. Let's say if your sample size is n, which is moderate, then you have this typical distribution. But once your n is large, then your distribution looks like this, and its mean value would be the same as the mean value of the original population from which the samples have been drawn. So this is actually the purpose of this central limit theorem. So central limit theorem allows you whatever distribution of the population distribution is, but if you take the sample means and your sample size is large, then your sampling distribution would be a normal distribution. And what do you mean by the large? We just simply say when your sample size is greater than 30, the sample mean is approximately normally distributed, regardless of the shape of the distribution of the population, which is under consideration. So irrespective of that, your sample mean distribution would be a normal distribution. So this is formally a central limit theorem is. And we can see, let's say we have certain distribution with mean and variance is there. What I do is I take different samples. Y1 bar is a mean value of from the same population, and Y2 bar is the mean of this population, and Y3 bar is another sample. And what I do is I have all these sample means, and if I plot it at one place, all these sample means would be distributed normally. So it was going to give you a normal distribution, and this normal distribution having a mean value mu, and the variance standard deviation would be sigma over under root n, or variance would be sigma square over n. So this would be the visual picture of the central limit theorem. Whatever your distribution is, if you take samples and each sample would have a different mean values, and if you plot the mean of that distribution, you end up with a normal distribution with the mean value is same as the population mean, and their variance would be sigma over under root n. And you can see another way. Let's say this time we have a population distribution is normally distributed, and if you take this x is my population, x bar is the sample mean. So if I draw the sample mean, even with the population with the sample size of 2, my variance has decreased. So if my and the distributions becomes normal, which is already normal, If you increase the sample size, what you're going to do is you are decreasing the variance, and the mean remains the same for the population as well as for the sample means. So here the sample means for a sample size of 10, your distribution lies the same and its variance is decreasing. So further increasing the sample size result into smaller variance with the same mean as the population mean is. If this is something we have elaborated, whatever your distribution is, if your sample size is greater than 30, then your sample mean distribution would be a normal distribution. Let's say if you have some other population like uniform distribution, if you take it as sample, then the resulting distribution for the sample mean would be this. If you increase the sample size, then your distribution looks like this. So at n 30 or greater than 30, whatever your population distribution is, your sample mean distribution would be a normal distribution. So that is actually the statement of the central limit theorem. Let's say another type of distribution, which is asymmetric distribution, representing a Poisson distribution sort of thing. And if you take a sample size of 2, then your sample mean distribution looks like this. If you increase the sample size, then for up to 30, you can see that whatever your parent distribution is, your sample mean distribution would result into a normal distribution. And this is true with, let's say, if you have this triangular distribution with your sample size 2, 4, and 25. Even for 25, you can have this normal distribution shape. If your population distribution is rectangular, then for different sample sizes, you can see the resulting distribution becomes a normal distribution. And let's say if you have this sort of distribution, and very interestingly, even if you have a population distribution with different modal values, two modal values, so and their sample size is 2, then the resulting distribution looks like this. If your sample size is 4, so if it is 25 or 30, then your sample mean distribution, this is x and this is x bar. So this is actually the sample mean distribution. Your sample mean distribution would look like a normal distribution. So whatever your parent distribution is, if your sample size is large, then the sample mean distribution would always be a normal distribution, and this is what the central limit theorem is all about. So okay, in sampling we already have seen that if let's say this is the distribution of the n items, so this is my population actually. This is my population with the whole population distribution represented by the green line. And let's say if we take the different samples, and if you see the sample distribution, its mean would be the same as the population mean, and its variance is sigma square over n, and this is we have analytically proved in the lecture of sampling distribution. And it obviously following, because original distribution is normal, and the sample distribution would also be normal distribution. So this is we already have seen in the earlier, but what exactly the central limit theorem is about. For example, if you have a distribution which is not a normal distribution, so here the green one is not a normal distribution, it is sort of an asymmetric distribution other than normal distribution. But if you take the sample and make the distribution of the sample means, then you result into a normal distribution. So this is actually representing the effect of the central limit theorem. But keep in mind, when n is sufficiently large, means at least greater than 10, 20 or 30, even in some of the parent distributions, even at sample size of 10 result into normal distribution, or sometimes it can go up to 25 or 30. But 30 is most of the time when your sample size is 30, then your sample mean distribution is always a normal distribution, whatever, irrespective of your parent distribution. Okay, now let's see this problem. The amount of a particular impurity in a batch of certain chemical product is a random variable. So the amount of impurity is a random variable, so it means it can take any value, and its average or mean value is 4 grams with standard deviation of 1.5 grams. So if 50 batches are independently prepared, what is the probability that the sample mean amount of impurity lies between 3.5 and 3.8 grams? So average is 4 grams, so we need to work out the probability between 3.5 and 3.8. So if you look at here, your random variable is you are actually taking 50 batches of independently prepared. So you have a large population and you have taken 50 samples. So here your sample size is much larger, greater than 25 or 30. Then we can consider it a central limit theorem to be applicable. So here x bar represents the average value of that random variable, and we know that the average value of the random variable would be normally distributed with mean value equal to the population mean, which is 4 gram, and its variance is variance for the sample mean would be sigma square over n, and here n is 50. So using this standard normal distribution table, I can calculate the probability that the sample mean would be between greater than 3.5 and less than 3.8. So I just calculate the z value, and from that z value, from the tables or from the graph, I can calculate the probability. And why I've used an approximate, because I don't know about it is justifiable to use the normal distribution to calculate the probability, because the amount of impurity, the population distribution for that particular impurity or parameter of interest, we have no idea. But using, thanks to this central limit theorem, we have considered the sample mean to be considered as normal distribution. So here 16.45, or from software 16.37, is the probability that your where your mean is 4 and your standard deviation is square root of 0.045, which is 0.121. This would be the this is how we can solve problems in which the parent distribution is not a normal distribution, but using the central limit theorem, we can calculate the probability using a standard normal distribution. So this is where I end this lecture.